Welcome to this explainer. Today we're going to completely demystify the incredibly complex and honestly, truly fascinating journey of cotton. It's a fiber that likely makes up exactly what you're wearing right now. We'll be tracing its path all the way from microscopic raw fiber testing in the lab through the massive, heavy machinery of the spinning mill, right down to the finished, tightly wound yarn. If you've ever found yourself wondering how fluffy white bales become perfectly uniform textile threads, well, you are definitely in the right place.
Let's just quickly run through our roadmap for this process. We're going to start with 1, the fiber quality foundation, then move into 2, HVI and APHIS testing explained, and define 3, crucial cotton fiber parameters. After that, we hit the factory floor for 4, the mechanical spinning journey, before wrapping things up with 5, final yarn quality metrics.
The big takeaway to keep in mind here is that everyday fabrics depend entirely on microscopic precision. Whether a mill is churning out a standard ring-spun cotton or some highly specialized performance blend, the physical and mechanical properties of the raw fiber dictate absolutely everything. They control the tensile strength, the processing efficiency on the floor, and ultimately, how the fabric you're wearing is going to look and feel.
All right, let's jump right into Section 1, the Fiber Quality Foundation.
So, testing cotton by hand? That is ancient history. Today, highly automated instruments act as the ultimate gatekeepers of the spinning mill. Think of it like a macro versus micro setup. On one side, we have HVI, or high-volume instrument. This is your rapid, bulk screener. It evaluates massive tufts of cotton in under 45 seconds, giving mills the macro overview they need to grade commercial bales and plan their processing. On the other hand, you've got APHIS, the Advanced Fiber Information System. APHIS is slower, but it acts as a highly precise, micro-level detective. It uses optical and electrostatic sensors to analyze fibers literally one by one, catching the tiny variations and rogue short fibers that a bulk test is just naturally going to miss.
Moving right along to Section 2, HVI and AFS testing explained. Let's zero in on what these gatekeepers are actually measuring before a single ounce of cotton is approved for the factory floor. What's super interesting is a metric called micronair. It's essentially pulling double duty. It doesn't just measure how thick a fiber is, it evaluates both fineness and maturity at the exact same time. The machine figures this out by pushing air through a specific mass of cotton and calculating the air permeability. This is incredibly critical. If a fiber is too fine or immature, it's just going to tangle up into these tiny, stubborn knots called neps. And trust me, those neps will absolutely ruin how the yarn absorbs dye later on.
Because of that, there's a very specific sweet spot for industry standards. Ideally, you want a micronair landing right between 3.5 and 4.9. If you dip below 3.0, you're looking at very fine, usually immature fibers that are going to cause major structural defects. But if you shoot up to 5.5 or higher, now it's way too coarse, making it almost impossible to spin a fine, high-quality yarn. You literally have to stay in that medium range for optimal spinning.
That brings us to Section 3, crucial cotton fiber parameters.
Beyond just fineness and maturity, the actual physical length of the fiber is paramount to surviving the spinning process. We evaluate length using the Uniformity Index, or UI. This is a percentage that compares the upper half mean length, which is the average length of the longer half of your fibers, to the overall average length of the whole sample. A high uniformity index, specifically anything above 80%, means your fiber lengths are highly consistent, and consistency translates directly into fewer breakages on the machines and a much smoother, significantly stronger yarn.
And naturally, that leads us right into short fiber content, or SFC. When APHIS maps out the length distribution of a sample, it's hunting for problematic short fibers, specifically anything under half an inch, or 12.7 millimeters. If your bulk sample has too high of a percentage in this short fiber zone, those tiny pieces simply won't hold together during the twisting process. They slip, they break, they increase fuzziness, and they will completely ruin a fine count yarn.
Let's head out to the factory floor. Section 4, the mechanical spinning journey.
All right, so the raw cotton passed the rigorous lab tests. We know we have good, uniform fiber. Now the real physical transformation begins. The fiber is about to run a relentless mechanical gauntlet, a progressive sequence that transitions it from tightly packed, dirty bales all the way into a perfectly twisted, continuous strand of yarn.
First stop, the blow room. Picture this. Bales of cotton are fed onto conveyor belts where massive mechanical beaters and powerful suction fans literally rip the compressed cotton wide open. The goal here is to thoroughly loosen the tufts, blend different bales together for consistency, and just beat out all the heavy trash. We're talking leaves, dust,
seed coat fragments, getting all that junk out before the fibers move forward. Next up is carding. Honestly, a lot of experts consider this the single most important operation in the entire mill. The open cotton feeds into a massive cylinder covered in millions of tiny wire teeth. These teeth act like a super intense, high-speed comb. They disentangle the chaotic clumps and force the individual fibers to lay perfectly parallel to one another. The cotton then exits the machine as a soft, continuous, untwisted rope known as a sliver. After that intense carding, we enter the drawing and roving stages. During drawing, several of those carded slivers are combined and pulled together to eliminate any lingering irregularities and perfectly align the fibers. Then, in the roving frame, this drafted sliver is stretched even further and given a very slight temporary twist, just to hold it together. Now, we have a much thinner strand, called a roving, which is finally small enough to feed into the spinning frame.
And at last, we arrive at the ring frame. This is where the magic happens. The roving feeds through drafting rollers that are turning at different speeds, which pulls or attenuates the strand down to its final desired thinness. Then, as it exits, it passes through a tiny metal guide called a traveler. This traveler is spinning rapidly around a circular ring on the spindle, sometimes reaching insane speeds of over 20,000 RPMs. That extreme rotational speed inserts the final permanent twist, completely locking those parallel fibers together into a highly cohesive, strong yarn.
Which brings us to our final step, Section 5, Final Yarn Quality Metrics.
The survivor of this intense mechanical journey must now return to the lab to be officially graded. You see, a spinning mill's overall success is ultimately mirrored by its yarn evenness. We measure this using two primary statistical indices, U%, or unevenness, and CV%, the coefficient of variation. Because cotton is a natural fiber, a yarn will never ever be a mathematically perfect cylinder. So these metrics calculate the ratio of maximum to minimum diameters along the yarn's length to detect any mass variations.
When we talk about U%, imagine a perfectly straight line representing the ideal mean thickness of the yarn. U% tracks the actual physical deviations, the jagged peaks and valleys of mass, along a test length. A lower U% means those peaks and valleys are minimal, meaning your yarn is highly consistent.
CV% takes that same concept but applies a standard deviation bell curve to the mass fluctuations. This is brilliant because it gives the quality control team a precise mathematical understanding of how consistently the ring frame performed during the final twist, immediately highlighting any recurring mechanical faults.
So what actually makes the grade? Well, to pass final inspection as a good quality yarn, you generally need a U% below 5% and a CV% below 8%. Now, if your U% creeps up to somewhere between 5 and 7%, it's still acceptable, but it's a huge warning sign that the drafting and twisting processes on the factory floor weren't flawlessly synchronized, or maybe your raw fiber just wasn't as uniform as you thought.
But we don't just stop at evenness. The yarn faces a total barrage of other tests. We test its tensile strength by breaking an entire skein to calculate the breaking load. We measure its elongation before snapping, check for protruding hairiness, and crucially, we count microscopic imperfections using the Classimat fault classification system. This standardized system categorizes every fault by size and length, hunting down thin places where the yarn is dangerously weak, thick places that could easily jam a weaving loom, and those pesky little neps we warned about earlier.
It really leaves you to step back and wonder just how incredibly interconnected this entire sequence is, right? I mean, how could a single microscopic short fiber detected by APHIS at the very beginning cascade into a major structural defect in the finished yarn? Well, when you trace a break in a final yarn back to its source, you often find a cluster of immature fibers that barely pass step 1. It just goes to show that absolute precision at the very beginning is literally the only way to guarantee perfection at the finish line.